Section 3.3 is titled The Theory of Equations, and we're continuing our discussion of what happens when we have different kinds of polynomials and looking for their solutions. Now, I've sort of mentioned this in passing, but not in a formal way yet. There's a connection between roots, or zeros, or x-intercepts, those are all the same things, and multiplicity. So if the factor x minus c occurs k times in the factorization of the polynomials, then we would actually say that c is a root of p of x, and it has multiplicity k. So I mentioned this last time when we were talking about the fact that if I have a degree 3 polynomial, I'll have 3 answers, but some of the answers might repeat themselves. That happens when I have exponents on those factors, okay? So, let me do that. I've got an example, but I know a few of you are still writing, so let me pause.
Theory of equations. Right?
Theory of equations, yeah. Just leave a space in your notes for right now, Maxwell, and you can go back and fill in that definition that they're writing down when we get done, okay? All right, so here's an example. And what we're talking about is these exponents here, okay? Now, there's an exponent, an understood exponent of 1 on the last term because there's nothing written there. But we're looking at those exponent locations. So if we're finding all of the zeros that exist with their multiplicities, then it means we set each factor equal to 0 and solve. So x cubed equals 0, I would take a cube root, so I would get x equals 0, right? And what I would write down next to it is that it has a multiplicity of 3 because its exponent's 3. On the second one, x minus 2 equals 0. I add my 2. So x equals 2. And what's its multiplicity? 2. Again, because the exponent here is a 2. That's where we're getting the multiplicity count for, okay? Multiplicity just means how many times does it happen? How many of them are there? Well, there's 2 of them because there's 2 factors there that are identical. And then the last one, x plus 4 equals 0. So it would be a multiplicity of 1, exactly. So x equals negative 4.
3 square root x to the third equals
0.
It's a cube root.
Yeah, it is a cube root. Sorry. I was trying to cram things in space-wise, and it wasn't working for me. Let me slip it over just a little bit, and we'll put it there. That's better. So cube root on both sides. So we end up with x equals 0 with a multiplicity of 3, x equals 2 with a multiplicity of 2, and then x equals negative 4 with a multiplicity of 1. So if it's already in factored form, that's very friendly. We just set each piece equal to 0 and solve. But we could start with something that's not already in factored form, like part B here, and we would do the factoring. So first of all, notice that they all have x in them, right? So we're going to pull out x. How many x's do they have in common? X cubed. So if I have x to the 5th, then I take out x cubed, what am I left with?
X squared.
Good. 6x. Keep going, Damaris, you're doing good.
Plus 9.
Okay. Awesome. Okay, so is everybody good with that? Pulled out the x cubed. And then we're going to factor the piece that remains, if it's possible. This one it is. So I have x and x. The signs have to be the same in order to get me a positive 9 here at the end, and the signs have to be negative to get a negative 6 in the middle. So negative and negative. What are the numbers that go at the end?
That's
3 and 3. So if I consolidate this for the type of problems we're working with, you see that there's an x minus 3 squared, right? Because it's there twice. So this first one, if I set it equal to 0, is just like their previous problem. I take the cube root of both sides and end up getting x equals 0. What's its multiplicity? Still 3, yeah. The other piece, x minus 3 equals 0. I add my 3. So x is 3. And what's its multiplicity? Multiplicity of 2. So that's the relationship between the exponents, really, and how many times we end up with them being roots. And they're called multiplicities. All right, some graphing facts. So what this slide's all about is what happens on a graph when you have multiplicities. So if it's a squared, if it's a cubed, if it's a power 4, how does that affect the shape of a graph? So let me read through it with you. I know you're going to write them down, but the graphing facts. The first one says, with multiplicities considered, a polynomial of degree n has n roots. We've already talked about that. I've said it today, and I've said it before today as well. Power 3, 3 roots. Power 7, 7 roots. The second one we haven't talked about, though we've seen it happen. Complex roots come in conjugate pairs. So remember yesterday when we had 1 plus I and 1 minus I? We had it happen twice. Both of the last two problems had that happen. They're conjugates of each other, and that always happens. If I have one piece, I have the other piece. The third fact, if the multiplicity of a root is odd, the graph crosses the x-axis. So what do I mean by crosses? I mean it flat out cuts through the x-axis. But if the multiplicity is even, so like imagine an x squared graph, a parabola, then the graph only touches or bounces off the axis. Right, so think about like a parabola that just touches down at the axis and goes back up. That happens when things are even roots or even multiplicities. All right, so we have a few examples of questions related to these concepts. So what we did in problem number 1, parts A and B, is we took an equation and we either factored or it was already factored. We set things equal to 0 and we said what the multiplicities were, right? Like that's what we did. What we're doing on problem number 2 is we're going backwards. We're actually given the zeros and we're going to create the polynomial. Now we've done a little bit of this before, but we didn't do it to the fullest extent that we're going to do it now. So if I have a 0 at 2, it means that x equals 2. Let me start it out this way. It means that x equals 4, and it means that x is equal to negative 3. Does that make sense? Yes? Okay, good. What we want to do is we want to set them each equal to 0, like move everything to the same side, like we would if we were solving a quadratic. So we're going to subtract the 2. So this is actually x minus 2 equals 0. We're going to subtract the 4. So this is x minus 4 equals 0. And add the 3. So this is x plus 3 equals 0. Is that part okay? Okay. What that tells me is that these 3 pieces are the 3 factors of my polynomial. In other words, I have x minus 2, x minus 4, and x plus 3. All equals 0. And then what do you think I need to do now? Foil or distribute it all back out, right? So take 2 at a time. We'll just take the first 2, just because I like moving from left to right when possible. And we're going to distribute or foil it back out. So I'm going to have first terms is x times x or x squared. Outside is negative 4x. inside's negative 2x, and last is 8. Okay, I need more space, so I'm shifting things around a little bit while you guys are writing that down. We'll consolidate what's here. So this is x squared minus 6x plus 8. And if you can consolidate as you multiply, that's fine too. And then we're going to multiply it through the the three-termed expression, the polynomial at the beginning times the 2 at the end. So there's not a FOIL method for doing that, but what I recommend doing is to take the first term and just distribute all of it first. So if I take x squared and I distribute it through, x squared times x is x cubed. X squared times 3 is 3x. Squared, sorry. And then we'll go on to doing that with the negative 6. So negative 6x times x is negative 6x squared. Negative 6x times 3 is negative 18x. And then with 8. 8 times x is 8x. 8 times 3 is 24. Okay. And then the last thing that I would need to do is to combine like terms. Give myself a tiny bit more space and we'll be good. So there's 1x cubed, so I have x cubed. I have positive 3 and negative 6x squared, which gives me negative 3x squared. I have negative 18x and positive 8x, which gives me negative 10x. And I have 24. Now, let me just mention something that you could do, because we've talked a little bit now about using your graphing calculator in an advantageous way to make sure that you got this right. You could put this equation, not the equals 0 part, everything else, into the y equals on your calculator, like on your TI-84s, right? And you could actually make sure that it crosses the graph at x equals 2, x equals 4, and x equals negative 3 visually. That's what you would be looking for. You'd be looking for it to actually cross through the graph at those points. It will. We did it right. But that's actually a check step that you could use if you would like. Okay, let's try another one. Next one's a little bit different than what we've seen at all before. This one had some similarities to something we've seen. The difference on part B is that I'm dealing with complex numbers, right? Or imaginary numbers. They don't actually work any differently, but somehow it feels a little bit different because you haven't done it with eyes. So we're going to do the same thing. We're going to start out x equals negative 9i and x equals positive 9i. And we're going to shift the values so that I have 0 on the right. So I'm going to add 9i. So x plus 9i equals 0. And the other one I'm going to subtract 9i. X minus 9i equals 0. Now, some of you are like, why are you writing that out? Why don't you just jump from here to here? Okay, if that's you, you can jump from there to there. That's fine. But I know that's not everybody, so I just want everybody to make sure they're seeing where I'm jumping from. I don't want them to be like, that leap did not work for me. Okay, so if you can leap there, go for it. What we're going to do then is we're going to put those two as factors in a polynomial. So x plus 9i, x minus 9i equals 0. And then we're going to multiply it back out. This one's kind of nice because I don't have three terms, or I cannot talk today. 3 factors. I only have 2 factors. So I really do just FOIL. X times x is x squared. X times negative 9i is negative 9ix or xi. And then the inside terms are positive 9ix or xi. And my last terms are negative 81 I squared. Okay, so far so good? Mm-hmm. So tell me something.
I squared technically just negative 1?
Yes, we're going to get there. Yes, that's one thing I wanted to make sure everybody noticed. So Maxwell's right. I squared is negative 1, so this is negative 81 times negative 1 at the end, or positive 81. What happens in the middle? They cancel, right? And that should make sense because these are conjugates, right? Whenever we multiply something by its conjugate, it cancels out. So that makes sense. And then my first piece was x squared. So this is actually x squared plus 81
Okay, why is
equals
that easier
0.
than like the normal number one? What the heck?
We had 3 terms, remember? Or 3 factors, remember? And the other reason it's easier is because we had conjugates on this one, right? Like differences of squares, and differences of squares cancel out middle terms. So that part's friendly.
I like that.
All right. It looks like the next one only has 2 terms. But it doesn't. I know that x is equal to 4, that's fine. And I know that x is equal to negative I, that's fine. But there was one piece over here that you wrote down in our, 5-minute time span of writing, right? That says complex roots come in conjugate pairs.
So you're gonna have to.
Is that
So-
1 plus I and 1 minus I?
Yes, so the 1 plus I, 1 minus I was an example of one where we saw earlier. But the same thing happens here. If there's an I, negative I, there's also a positive I. So whether they tell you that there is or not, there is, because they have to come in conjugate pairs. So if I've got x equals I, I've also got x equals negative I.
Wait, so why isn't there a negative 4?
Because it's not complex. It's a real number. That's why. Yeah, so the i's are different in this regard. Okay, so again, if I'm moving things over, this one's going to give me x minus 4 equals 0. This one's going to give me x minus I equals 0. And this one's going to give me x plus I equals 0. Those are, I'm going to end up with 3 factors this time. So I have x minus 4, I have x minus I, and I have x plus I. Now, mentioned on the last problem, when possible, I usually move from left to right. I'm multiplying these out, right? I said that on part A of this example set. I could move from left to right, and I could do that here, but that would not be the easiest way to do this problem.
You should get rid of the complex.
I need to get rid of the complex ones first. So these two being multiplied together is the most advantageous way to go. It'll work the other way, but it'll be faster this way. And the reason is because I will have things cancel out. I'll have x squared, I'll have plus ix, and I'll have minus ix, and then minus I squared.
So can we just put x squared minus 1?
Yep,
I mean plus 1.
plus 1. Good correction. So this is x squared. These add to 0. And this minus I squared is minus a negative 1, right? So I have plus 1. So this is x squared plus 1 and x minus 4. So we'll distribute out now. So FOIL again. X times x squared is x cubed. X times 1 is x. Negative 4 times x squared would be negative 4x squared, and negative 4 times 1 would be negative 4. I'm okay with you leaving it like this. It's not going to hurt my feelings none. That's fine. My math lab's probably going to make you put it in order from least to greatest to least on the exponents. So it'll probably make you reorganize them with it to being x cubed minus 4x squared plus x minus 4. And I need to go back and add something in that I haven't done on any of the ones before, but I should. It wanted to have, how did it phrase it? A polynomial equation, and so we wrote equals 0 here. I did do it on both of them before, so here's an equals 0 here. It might want you to say equals y, that would be fine, or equals f of x as well, that's fine. But this would be an equation that would satisfy the conditions. Okay, I have one more example. We're going to finish up right on time, okay? And then I'll hand out your test as you leave. All right, I have 7 plus I, and I have 3. What's missing? There's also a 7 minus I. Yes, there is. Okay, now I'm going to put the x minus 3 first. I'm sorry, x equals 3 first. And then I have an x equals 7 plus I, and I have an x equals 7 minus I. So if I move the 3, I've got x minus 3 equals 0. I have to move the 7 and the I, so I actually have x minus 7 minus I equals 0. And I have x minus 7 plus I equals 0? Because I have to subtract both of the pieces or add both of the pieces to the other side. That one's a little bit different. We haven't had that happen yet. All right. So we have x minus 3. I have x minus 7 minus I. And I have x minus 7 plus I.
Can we make it a -1 that I written?
We can't because I is not -1, it's I squared. So we'll have an I squared in a moment that we'll do that with, Damaris, but we're not quite there yet. So we'll save our x minus 3 till the end. And this is actually, right, a trinomial, 3 terms times 3 terms, right? So I'm not going to be able to FOIL per se. I'm going to have to distribute it out much like I did in an earlier problem. So I'm going to take this x and I'm going to multiply it through everything. So I'm going to get x squared minus 7x and plus ix. Now we're going to do that with the 7. I have negative 7x. I have positive 49. And now I have negative 7i. Trust me, all the i's are going to go away before I'm all said and done. But it's a little messier process on this one. And then distributing the negative I through. So I have negative ix, positive 7i, and then negative I squared. So there's that I squared you're asking about, Damaris. It is showing up at the very end. All right, so let's pair things up. I have a ix and a negative ix. I have a negative 7i and a positive 7i. And this piece here at the end is the one that will be plus 1. Okay? Now, there's some other pieces that will simplify. So we already said this is plus 1. Let me write it in. There's an x squared. I have negative 7x and negative 7x, so it's negative 14x. And then I have 49, and I have 1, so I have 50. And now I have to distribute through 3 terms again, right? I don't have 2 terms to 2 times 2 terms one more time. So this x goes through. X times x squared is x cubed. X times negative 14x is negative 14x squared. X times 50 would be 50x. And then we'll go through with our negative 3. Negative 3 times x squared is negative 3x squared. Negative 3 times negative 14 is positive 42x. And then negative 3 times 50 is negative 150. All right. It's not pretty, but it's almost done, right? So we have x cubed. I have negative 14x squared and negative 3x squared, which gives me negative 17x squared. I have positive 50x and positive 42x, which gives me, 92x. And then I have my negative 150. Okay, so let's say you wanted to check this one, right? Or even the last one. And you're like, okay, well, how could I use my calculator to check them? You can check part of what's going on. You can't check all of it. The part that you can check is you can check to make sure that the only real 0 is 3, right? Because the graph should cross at 3, and it shouldn't cross anywhere else. So you could confirm at least that much of what you did being correct. And if you didn't see it crossing at 3, or if you saw it crossing somewhere else, then there's mistakes in your work. All right, so this assignment will be assigned to be due on Monday.